Hi. So this is like my fifth time recording this one because I don't know why I keep having issues today. I keep messing up pausing the wrong thing. So I guess I'm just gonna try and go through this without doing any pauses. Um, so we're gonna look at derivatives of trig functions today. Specifically, I'm going to find the derivative of sine based on that example, right? Because I'm going to use the definition of the derivative. You're going to see our limits pop up. I'm going to go through all that work, find the derivative of sine from scratch. And from that, I would like you to find the derivative of cosine from scratch. Once you have these two derivatives, if you have the derivative of sine in your belt and you have the derivative of cosine in your belt, once you know what it is, as you've seen, you don't need to find it from scratch every single time. Just use it. You know what it is. And therefore, you could find the derivatives of the other four trig functions, right? Tangent, secant, cosecant, and cotangent, because these four are all just ratios of sine and cosine, right? Tangent of x is sine over cosine. And so if you know the derivative of sine, you know the derivative of cosine, right? You can just use your quotient rule to find the derivative of tangent. And then once you know the derivative of tangent, you don't have to do it this way anymore. You can just go straight to your answer. But I want us to kind of discover them today rather than just here's a list of formulas. I really enjoy knowing that you've seen a little bit of the reasoning and you can have a little more confidence in where these derivatives came from. Okay, so I've already done this in the packet that I posted on the website, but like I'm gonna go through this derivation in this video because I think it might be a little bit easier to follow. But it's the same information that's in the packet, nothing new. Okay, so that's what we're gonna do. In order to do it, there's two limits that we need to know. Actually, let's do it in different colors. So this first limit is the limit of sine of stuff over stuff as that stuff goes to 0. Why did I write it like that? Because I'm really emphasizing here that whatever stuff you put inside the sign, this limit only works if it's copy and pasted here. Like these two parts inside the sign and in the denominator, they must be identical. And then all of it must be going to 0. This, and this technically should look exactly the same for this limit to work. And if you do have that, then you know that that limit is equal to 1. So that's one limit. The second limit that's going to come into handy is the limit of 1 minus cosine of stuff over stuff as that stuff goes to 0. Again, copy and paste. So if you got anything inside this cosine, then it's going to be copy and pasted here and copy and pasted there. Okay, it doesn't matter what it is. They're just all of those three pieces need to look identical. And if you have that, then this limit is equal to 0. Now in the packet, it notes that you can prove these limits using some geometry and squeeze theorem. You can also just confirm by graphing, right? Like if you go on GeoGebra or Desmos, GeoGebra, and just graph y equals sine of x over x. Graphically, you can see what happens as x goes to 0, right? This function will go to 1. Similarly, you can graph 1 minus cosine of x over x and see what happens as x goes to 0, and this thing should go to 0. So if you're like, where'd these limits come from? I would highly suggest just looking at the graphs. But since we know this is true, we're going to try and use these because they're going to pop up while we take the derivative. So we're going to try and find the derivative of sine. Then we know in order to do that from scratch, we're going to use our limit definition, which is the limit as h goes to 0 of sine of x plus h minus sine x all over h, right? That's the limit definition of the derivative. And a lot of the times our goal was to get rid of the h. If you recall when we did the derivative of e to the x, we didn't get rid of the h. We ended up with the limit as h goes to 0 of this, and it was something that we knew was equal to 1. And so really what our goal was there is, can I find this limit hidden anywhere, right? If you remember how we did e to the x, that's sort of the same approach we're going to take here. Is we're going to be keeping these limits in mind. Okay, so we're going to maybe want to write them off to the side here. So limit as I'm thinking as h goes to 0 in this case. So I'll be looking for sine of h over h. I'll want to keep an eye out for this. And I want to keep an eye out for this limit. So if I can find those floating in my derivative limit over here, that's probably going to be helpful to me. And so I'm thinking that's the strategy. Okay. So based on what we're starting with, this thing right here, I feel like I don't really want x plus h. I just want sine of h. So the question is, how can I get the h to come outside of the sine? And so if you look at what we have, sine of x plus h, the fact that x and h are inside, right? Anything inside a sine of blah, those are angles in there. Angles have to go in. And so that means that the x and the h that we have right here are technically two angles added together. And there's a formula for sine angle addition. And so that's something that we want to write out and look at carefully. So if I have sine of alpha plus beta, for example, the formula is sine of alpha cosine beta, right? So sine of the first thing, cosine of the second thing, plus sine of the second thing, cosine of the first thing. Here's my first thing, here's my second thing, right? My second angle, first angle. So we just need to replace these. So if I have sine of x plus h, that should be sine of the first thing, cosine of the second thing, plus sine of the second thing, cosine of the first thing. And if I do that, I can see, oh, hey, I get a sine of h, and that's something that I was probably looking for. I also get a cosine of h, which is something that I was looking for. So I'm thinking we definitely want to do the angle addition here. And so that's what we will do. Limit as h goes to 0, sine of x, cosine of h, plus sine of h, cosine of x, minus sine of x, all over h. Make that a little nicer. Okay, and so again, keeping in mind the limits that we're looking for, I kind of see this part right here, right? Sine of h over h, do you see that right here? There's a cosine attached to it, but it's part of what I want. I also have a 1 minus cosine h over h. I don't see that one quite yet, but here's the cosine of h, and here's the h, right? But I want it to be 1 minus cosine. So I'm looking for that. Maybe for now, let's just rewrite it. Oops. Let's move this part in front because we already know that that's something of interest, right? All over h. And then I have left sine of x cosine of h minus sine of x over h. So I've kind of separated them, right? Because I was pulling the piece that looks like this limit so that it was looking even more like my limit. And I kind of have my leftovers here. And now that I've rewrote it this way, do you see how both of these have a sine of x in common? That's kind of nice because I'm thinking if I factor out the sine of x, then I'll probably get something that looks like this, which is what I want ultimately. So it was kind of good that I rewrote it that way because now I really see, hey, these have a common factor. Let's go ahead and factor that out, right? So we're going to factor the sine of x out. And in fact, I'm going to go ahead and factor out a negative sine of x because that'll make it look like this. If I just factor out a sine, I see that I'm going to have cosine of h minus 1. So if I want it flipped, I better pull out a negative. Okay, so we're going to get limit as h goes to 0 of sine of h cosine of x. Okay, I'm factoring out a negative sine of x. And so that'll give me a negative cosine h plus 1, which is definitely 1 minus cosine of h that I wanted over h. And this was a plus in here, but if I'm plusing a negative, I can just rewrite that as minus. All right, and so don't forget I'm taking the limit of everything. And I think this is pretty much it. So I'm going to go ahead to the next page and wrap this up. I'm hoping that you all can see it. So if I have the limit of this minus this, right? I can think of that as two separate limits. Limit as h goes to 0 of this thing minus limit as h goes to 0 of this thing. And here are my golden tickets right here. Right? Got the limit as h goes to 0 of 1 minus cosine h over h. And then I have the limit as h goes to 0 of sine of h over h. And the stuff that's left, right, these things, they don't have h's in them at all. So I know that they're not affected by my limit. And so I don't have to worry too much that they're you know, attached, because they're not, the limit doesn't really do anything to them. So they're just along for the ride. I can really focus on this, right? And just simplify from there. So the limit as h goes to 0 of this, we know, right, as long as this, this, and this are all copies, this is going to 1. And the limit as h goes to 0 of this stuff, 1 minus cosine of h over h, that is going to go to 0. And so we're going to get 1. Let's do that in color. Okay, so we're going to get 1 times cosine of x minus 0 times sine of x. Well, 0 times anything is 0. So this is just 1 times cosine, which is cosine of x. So that means the derivative of sine is cosine. Cool. So based on this, you should be able to do on your own the derivative of cosine. And we'll talk about that on Thursday. The other thing, well, once you find the derivative of cosine, I also encourage you to try to find the other trig functions. But the other thing that I want to point out is if we know y equals sine, that graph actually looks something like this, pi over 2 up at 1, pi over 2, this is pi, this is 0. If I'm looking at y prime, which we know is cosine, y prime means the slope of tangent lines, right? So if I wanted to just graph this, I could maybe try to imagine what are the slopes of all my tangent lines at different points. So if I think of 0, right, if I draw a tangent line right here, the slope of this, if you zoom in really, really, really far on GeoGebra or Desmos or some computer graph, you'll find that at 0, the slope is positive 1. What about at pi over 2? What is that tangent line. That looks like this, right? What slope is that going to be? That's definitely going to be 0. Then we can look at pi. So that tangent line is going to look something like this. And if you zoom in really closely, you're going to see that the slope of that is -1. Then we can check 3 pi over 2. If you go there, again, that slope is going to be 0. And obviously that's only 4 points, but you can kind of see that if we take those ideas, okay, 0 up at 1, pi over 2, 0, pi -1, 3 pi over 2, 0. That is exactly, precisely the way that cosine curve starts going. And if we start plugging in more, you would definitely see, right? The cosine graph appear, because we're going to hit 0 at -pi over 2. Boom. Then we're going to be at -1 at -pi. Boom, down at -1. Okay. And so these values, -1, 0, 1, 0, -1, 0, are the y values that show up on the graph of the derivative. And so this should make us feel happy that this idea of slope of tangent lines is consistent with the derivative that we found over here. Okay, so that's it. Your task, like I said, is to find the derivative of cosine of x, and then I want you to find the derivative of tangent of x. And please try, if you have time, try to find these ones as well. Okay, but you should be able to get these two. Okay, so good luck, and we will discuss the rest when we meet again.